In the laboratory of systems biology, we try to understand the operation of the immune system by combining methods such as imaging, informatic analysis, and computational modeling. We thought the NOD-like receptor family of innate sensors was really ripe for such approaches, since only a few members had been studied intensively to date. The idea was to create many different NLR by making spontaneously active mutants, and then we could probe the cells in which we express these proteins for transcriptional changes that could informatically be mined to gain insight into the function of these molecules.
That strategy required me to carefully assess each NLR to determine how best to create the activating mutations, and while doing this, I found a putative mitochondrial localization signal in NLRP3.
The dominant paradigm when we started this study was that NLRP3 is activated by stimuli that promote its self-association. This leads to recruitment and oligomerization of the adaptive protein ASC that in turn recruits and activates procaspase-1. This protease then cleaves pro-IL-1 beta to its active secreted form, the cytokine IL-1 beta. NLRP3 and ASC are cytosolic proteins, and therefore the assembly of the inflammasome was believed to occur in the cytosol. But Neha's informatic analysis suggested the possibility that NLRP3 mitochondrial localization could be important.
This was intriguing because organelle recruitment is well recognized for TLRs and for the Rig-like helicases that engage the outer mitochondrial membrane protein MAVS. We therefore hypothesized that mitochondria might serve as platforms for NLRP3 inflammasome assembly and activation. Using confocal imaging, I found that NLRP3 was cytosolic until an activating ligand was added, at which point the NLRP3 associated with mitochondria. A mutagenesis study conducted with the help of our collaborator Kannan Natarajan showed that the N-terminus of NLRP3 was necessary for its mitochondrial localization and for oligomerization of ASC.
What mediated this recruitment? Based on several clues in the literature, we examined the roles of MAVS, a mitochondrial protein that plays a crucial role in Rig-like receptor or RLR signaling.
Using siRNA knockdown, I observed a clear dependence on MAVS for NLRP3 association with mitochondria, and biochemical studies showed that such association with MAVS was mediated with the N-terminus of NLRP3.
Was this MAV-dependent mitochondrial recruitment relevant for NLRP3 function in vivo? In vitro responses to crystalline activators of the NLRP3 inflammasome were largely independent of MAVS, and MAVS-deficient mice didn't show any consistent protection in a uric acid crystal peritonitis model.
We did, however, observe a dose-dependent role in vitro for MAVS in inflammasome activation in response to non-crystalline activators, and to see if this had in vivo relevance, we used a model of NLRP3 inflammasome-dependent acute renal tubular necrosis with help from a nephrologist in our group, Dr. Menaklat Worthy. Remarkably, MAVS-deficient mice were as protected from disease as ASC-deficient mice.
Together, these data supported a modified mitochondrial model of NLRP3 inflammasome activation. NLRP3 and ASC are cytosolic in the resting state. Non-crystalline stimuli cause release of NLRP3 from its autorepressed state, and this is followed by self-association. This partially oligomerized NLRP3 is then recruited to mitochondria via interaction with the adaptor MAVS. Mitochondria then serve as platforms for more efficient solid-phase oligomerization of NLRP3, and this promotes highly effective recruitment of the cytosolic adaptor protein, ASC, and then procaspase-1, which in turn becomes active and cleaves pro-IL-1 beta to its functional form.
These data changed the prevailing inflammasome model from one involving a single adapter protein to one in which at least two adapters, ASC and MAVS, are required for optimal response to non-crystalline activators.
These findings may be just the beginning of a new understanding of the role played by additional mitochondrial proteins in inflammasome function. Our results show that MAVS plays an important amplifying role in response to non-crystalline activators, leaving future studies to address the issue of how crystalline inducers stimulate this pathway. Also, because a number of diseases linked to the NLRP3 inflammasome involve mitochondrial dysfunction, future studies may provide evidence that there could be value in targeting the NLRP3 inflammasome for therapeutic benefit in these situations.